Today we shall solve a problem which is taken from sequence. Here the problem is a sequence un is defined by u1 greater than 0 and a sequential relation for the sequence un is un plus 1 equal to 3 times 1 plus un over 5 plus un for all n greater equal to 1. We have to prove two statements. First statement is un is monotonically decreasing and bounded below under the condition u1 greater than 1, and second statement we have to prove second statement which is also for u1 greater than 1 limit un equal to 1. There are two statements which are to be proved under the condition u1 greater than 1 for the sequence un is defined by u1 greater than 0 and un plus 1 equal to 3 times 1 plus un over 5 plus un for all n greater equal to 1. Now let us start. Here the sequence is defined by u1 greater than 0. At first we write u1 greater than 0, u1 greater than 0, then u2 equal to, we can get u2 from this relation by putting n equal to 1 on both sides of this relation. We get u2 equal to 3 into 1 plus u1 over 5 plus u1. This is also greater than 0 because u1 greater than 0. u1 greater than 0, so 1 plus u1 is positive, 5 plus u1 is positive, 3 positive, so this term will be positive, that is greater than 0. And also u3 equal to, we can write u3 from this relation which is 1 plus 3 times 1 plus u2, 5 divided by 5 plus u2, which is also greater than 0, as we have proved u2 greater than 0, as u2 greater than 0, and so on. We can easily verify that un, the sequence un, all terms of the sequence is greater than 0, that is un greater than 0 for all n belongs to the set of natural number. So also it can be easily verified that also it can be easily verified that all terms of the sequence greater than 0, that is un greater than 0 for all n belongs to the set of natural number. This can be easily proved, that is which is un greater than 0 for all n belongs to the set of natural number. Our proof, there are two proofs. First proof is un is monotonically decreasing and bounded below under the condition u1 greater than 1. We have to firstly prove un is monotonically decreasing and bounded below under the condition u1 greater than 1. So at first we write the condition u1 greater than 1. u1 greater than 1. If u1 greater than 1, then u2 minus 1 equal to u2 is this, that is 3 times 1 plus u1 over 5 plus u1 minus 1, which is equal to 2u1 minus 2 over 5 plus u1, 2 into u1 minus 1 over 5 plus u1. But u1 greater than 1, so u1 minus 1 is positive, that is greater than 0. This is also positive, greater than 0, this positive, so this term will be positive. This is positive as u1 greater than 1 implies u1 minus 1 greater than 0, and also u1 greater than 0. So this term, the 5 plus u1 positive, 2 positive, and u1 minus 1 is positive, so this term will be positive, that is u2 minus 1 greater than 0. So we can write u2 greater than 1, u2 greater than 1. We have got u2 greater than 1. Now we can prove that all terms of the sequence also greater than 1, that is un greater than 1 for all n belongs to the set of natural number. We can also prove un greater than 1 for all n belongs to the set of natural number. How can it be proved? It can be proved by method of mathematical induction. We can prove it by mathematical induction. To follow the mathematical induction, we can prove un also greater than 1 for all n belongs to the set of natural number. We can prove un greater than 1 for all n belongs to the set of natural number. It can be proved by using method of mathematical induction. To follow the mathematical induction, by using mathematical induction, so to follow the mathematical induction, to follow the MI, that is mathematical induction, at first we can assume un greater than 1 for n equal to k. We can assume un greater than 1 for n equal to k, that is uk greater than 1 is true, that is un greater than 1 n equal to k is true, is assumed, and then we have to prove that un greater than 1 for n equal to k plus 1. This is the method of mathematical induction. Next we have to prove un greater than 1 for n equal to k plus 1, un greater than 1 for n equal to k is assumed. Next we have to prove, to follow the mathematical induction. This is the process of mathematical induction. Next we have to prove un greater than 1 for n equal to k plus 1, that is un greater than 1 for n equal to k plus 1 is true. This is to be proved, and we have assumed un greater than 1 for n equal to k is true. We have to prove un greater than 1 for n equal to k plus 1 is true. Now uk plus 1 minus 1 equal to, uk plus 1 is taken from this relation, uk plus 1 equal to 3 times 1 plus uk over 5 plus uk minus 1. Here also for n equal to k, un greater than 1 means uk greater than 1, uk greater than 1. This is assumed. We have to prove uk plus 1 greater than 1, that is uk plus 1 minus 1 is positive. We have to prove it. Now we have uk plus 1 minus 1 is this. We can simplify it. uk plus 1 minus 1 equal to this is equal to 2 uk minus 2 over 5 plus uk, which is equal to 2 times uk minus 1 over 5 plus uk. This is also greater than 0, as uk greater than 1 imply uk minus 1 greater than 0. We have assumed uk greater than 1. So, uk minus 1 greater than 0. So, as uk minus 1 greater than 0, so this term is also greater than 0, that is uk plus 1. So, uk plus 1 minus 1 greater than 0, that is uk plus 1 greater than 1. So, we have proved uk plus 1 greater than 1. We have assumed uk greater than 1. Next, we have proved uk plus 1 greater than 1. This is the method of mathematical induction. By the principle of mathematical induction, we can say, so by the principle of mathematical induction, we can say that un greater than 1 for all n belongs to the set of natural number. For every n, un greater than 1. For every n, for each n, un greater than 1, that is all term of the sequence is greater than 1. That means the sequence is bounded below. This means the sequence is bounded below, because un greater than 1 for all n belongs to the set of natural number. Every terms of the sequence un is greater than 1, that is 1 is the lower bound of the sequence un. So, we can say un greater than 1 means un is bounded below. Sequence un is bounded below. So, therefore, sequence un is bounded below, because every term of the sequence is greater than 1, that is 1 is the lower bound of the sequence. So, we can say un is bounded below. So, we can say un is bounded below. So, we have one part of the first statement proved. We have proved the one part of the first statement. One part of the first statement was the sequence is bounded below. We have to prove sequence is bounded below. So, we have already proved un is bounded below. We have proved un is bounded below. Next, we have to prove un is monotonically decreasing sequence. We have to prove un is monotonically decreasing sequence. Now, we have to prove un is monotonically decreasing sequence. What is monotonically decreasing sequence? If un is monotonically decreasing sequence, then un plus 1 is greater than, un plus 1 is less than un. Then un plus 1 is less than un. If un plus 1 is less than un for all n belongs to the set of natural number, then this sequence un is called monotonically decreasing sequence. Every sequence un is called monotonically decreasing if un plus 1 less than un for all n belongs to the set of natural number. So, we have to prove that un plus 1 is less than un for all n belongs to the set of natural number. If we can prove it, then we can conclude that the sequence is monotonically decreasing. So, monotonically decreasing sequence, that is, we have to prove that is we have to prove un plus 1 less than un for all n belongs to the set of natural number. If we can prove it, that is un plus 1 less than un for all n belongs to the set of natural number, then we can say the sequence is monotonically decreasing. Also this sequence is strictly monotonically decreasing. This means the sequence is strictly monotonically decreasing sequence. Now un plus 1 now un plus 1 minus un equal to un plus 1 is this, that is 3 times 1 plus un over 5 plus un minus un. If we simplify it, we get 3 un minus 5 un, 3 minus 2 un minus un square. This is over 5 plus un. This is equal to 3 plus un into 1 minus un, 5 plus un. This is less than 0 because we have already proved un is greater than 1 for all n belongs to the set of natural number. So because as un greater than 1 for all n belongs to the set of natural number, we have already proved this. This is proved. This is previously proved. This is already proved. Un greater than 1 for all n belongs to the set of natural number. This means, that is this implies un minus 1 greater than 0, that is 1 minus un. This also implies 1 minus un less than 0. 1 minus un less than 0, because we have already proved un greater than 1 for all n belongs to the set of natural number, that is un is bounded below. This sequence is bounded below, which is already proved. This statement is already proved. So we can write 1 minus un less than 0. As 1 minus un less than 0, this is negative, but these two terms are positive because un is greater than 0. This is positive, but this is negative. So this term will be negative. That is un plus 1 minus un less than 0 for all n belongs to the set of natural number. That is un plus 1 less than un for all n belongs to the set of natural number. That is the sequence is monotonically decreasing, also strictly monotonically decreasing. So un is monotonically decreasing, also strictly monotonically decreasing. Sequence. So we have proved un is monotonically decreasing and un is bounded below. So we have proved so under the condition u1 greater than 1, so un, so sequence un is monotonically decreasing sequence, monotonically decreasing, we have already proved, and we have already proved also un is bounded below. The sequence un is bounded below because un greater than 1 for all n belongs to the set of natural number, and 1 is the lower bound of the sequence. So, we can say un is monotonically decreasing and bounded below. Un is monotonically decreasing and bounded below. We have proved this. We have proved un is monotonically decreasing and bounded below when also under the condition u1 greater than 1. We have proved the first statement. From this statement we can conclude that the sequence is convergent, because we know every monotonically decreasing and bounded below sequence is convergent. If a sequence is monotonically decreasing and bounded below, then this sequence is also convergent. Convergent means the sequence has a limit point, the sequence has a final. We can say therefore as the sequence is monotonically decreasing and bounded below, every monotonically decreasing and bounded below, every sequence which is monotonically decreasing and bounded below, this sequence will be convergent. Therefore, un is convergent. Convergent means the sequence, when a sequence is convergent, then this sequence has a limit. Yes. Then limit un exists. Suppose L. We can assume the limit as L because limit un exists, because the sequence is convergent. Every convergent sequence has a limit, definite limit. This definite limit is assumed as L, that is limit un exists, and this limit will be a finite number, that is L exists, that is the limit un exists as the sequence is convergent. Every convergent sequence have a limit un. Now we can apply this sequential relation. We have the sequential relation is, which is un plus 1 equal to 3 into 1 plus un over 5 plus un. We can take this sequential relation and we can apply a limit process on the both sides of this sequential relation. We can apply limit process on both sides of this sequential relation. So we can write limit un plus 1 equal to limit 3 times 1 plus un over 5 plus un. We can also write 3 1 plus limit un over 5 plus limit un. Limit un plus 1, limit un means limit n tends to infinity un plus 1, and limit n tends to infinity un. Also limit un equal to limit, also limit un plus 1 equal to limit un equal to L, because these are un plus 1 and un are the terms of the same sequence un. So limit un plus 1 equal to limit un equal to L, the same limit. So we can write it, and we can put the limit in this relation. Limit un plus 1 equal to L equal to 3 into 1 plus limit un equal to L over 5L. This is so. So we have L equal to 3 into 1 plus L over 5 plus L, that is L square plus 5L equal to 3 plus 3L, L square plus 2L minus 3 equal to 0. We can factorize this polynomial. After factorization we get L plus 3 into L minus 1 equal to 0. So L minus 1 equal to 0, that is L equal to 1, but L plus 3 is not equal to 0. But if we assume L plus 3 equal to 0, then L equal to minus 3, it cannot be possible because L is positive as all terms of the sequence are positive. So limit also will be positive. So L cannot be negative. But if L plus 3 equal to 0 is assumed, then L equal to minus 3, which is not possible. So L plus 3 cannot be 0. L plus 3 is non-zero. So only we have L minus 1 equal to 0 from of these two factors of the polynomial. Only one factor, that is L minus 1 of this polynomial is 0, that is L minus 1 equal to 0, that is L equal to 1, but other factor cannot be 0. So L equal to 1. Therefore limit un equal to L equal to 1. So we have proved two statements. First statement was un is monotonically decreasing and bounded below. We have already proved, and at last we have proved limit un equal to L equal to 1. Lastly we have proved limit un equal to 1, and previously we have proved un is monotonically decreasing and bounded below.